Today, we're going to continue to look at vectors, and we're going to start off with a nice straightforward example. A plane is flying into the wind. The plane's airspeed, that's what the plane thinks it's doing, is 500 miles per hour due east. So that's what the plane thinks it's doing. But there's a wind blowing 40 miles per hour to the northwest. So that's blowing in and across the plane, the front of the plane. And so we want to figure out what's actually happening to the plane. So that'll be the plane's ground speed and the heading. So those are the two components of what the plane is actually doing. All right, so let's draw a picture of what's going on so we can break everything into components. Specifically, we want to look at the components. The ground speed is what we would observe the plane to be doing. So the plane thinks it's going 500 miles per hour due east. But the wind is pushing into the plane, and that's going to, in this case, since it's pushing at the front of the plane, it's going to slow the plane down. So us standing on the ground would observe the plane moving at some not due east angle and slower than 500 miles per hour. So we would observe the plane going slower than 500 miles per hour. All right, so there's what the plane thinks it's doing, that's its airspeed, and what the plane is actually doing, that's its ground speed, and also its new heading because of the wind. So let's draw this draw the plane and the wind as a couple of vectors, because the plane's actual heading is going to be the sum of its airspeed, what it thinks it's doing, and what the wind is doing. So let's draw a picture for the plane. So the plane says, all the instruments on the plane are saying we are going 500 miles an hour due east. So I'm going to draw a vector for the airspeed. But the wind is blowing 40 miles per hour to the northwest. So I'm going to draw the wind starting from the front of the plane, and I'm just going to go to the northwest. Why didn't I end this at like an actual spot? I have a grid on my paper. And I picked northwest because it's a nice 45-degree angle that I can easily draw. So the wind is blowing 40 miles per hour to the northwest. So I'm just going, or 40 miles an hour. So I'm just going to draw it at a 45-degree angle. And then we can see that the sum of these vectors is what the plane is actually going to be doing. So we have a ground speed and we have some heading. I think the heading should be measured from north. So instead of the angle, we'll just, instead of heading, we'll just call that angle. I'm sure actual pilots can correct me in the comments. I care less about the calling it the proper thing and more about the fact that we're going to break things into vectors. So I'm going to take this, I'm going to write this airspeed as a vector. And this vector is all horizontal. And so I'm going to say this is 500 I hat and 0 j hat. I'm just going to break the airspeed into components. It's all horizontal. I'm going to use the usual, right to the right is positive and up is positive. So we're doing 500 horizontal and 0 vertical. The wind, we'll say, is at a 45-degree angle So the wind is going to be at 45 degrees, or pi over 4 radians for those of you who like real numbers. We're going to break the wind into its two components, a horizontal component and a vertical component. So we got this 45-degree angle. If we just separate the wind into its two components, I've got a magnitude of 40 miles per hour, and it's at 45 degrees. So I have a vertical component and a horizontal component. And I just realized I said those in the opposite order. I have a horizontal component, and now I have this orange vertical component. So my horizontal component will be 40 miles per hour multiplied by √2/2, because I've got an isosceles right triangle. The horizontal component will be the magnitude times the cosine of 45. So the horizontal component will be 40 times the cosine of 45 degrees. And the vertical component will be 40 times the sine of 45 degrees. In this case, sine and cosine are both √2/2. So my horizontal component will be 20 √2, and my vertical component will be also 20 times the square root of 2. So when I write the components of the wind, my horizontal component is going to the left, so I'm going to call it negative. So my wind vector is going to be negative 20 √2 and a positive 20 √2 negative 20 √2 I plus 20 times the square root of 2 j. Now, if we want the sum of those two vectors, I just need to add the corresponding components. So v plus w is going to be 500 minus 20 square root of 2 I, 0 plus 20 square root of 2 times j. So here's a vector describing what the plane is actually doing, what we observe the plane to be doing. So 20 square root of 2 is about 28.3. So 500 minus 28.3 is 471.7. So the vector for the plane is 471.7 I plus 28.3 j. So here's a vector that describes what the plane is doing. If we want the ground speed of the vector of the plane, we can just find the magnitude of this vector. So now the magnitude of v plus w will be the square root of 471.7 squared plus 28.3 squared. So 472.5. So I'm going to round it to the nearest tenth for no reason other than that's just what occurred to me to do, which is extra funny because just yesterday I was talking to my trigonometry class about rounding and significant figures. So yes, question in the chat, V plus W in purple is the displacement. So once I have the vector names, the ground speed part is going to be V plus W. If I want to figure out the angle, the angle is going to be based on the tangent because I have two components, a horizontal and a vertical component. So if I pull this out into a right triangle, if I pull this vector into a right triangle, I've got 471.7 and a 28.3 vertical. So if I want to find this angle theta, 28.3 will be opposite theta and 471.7 will be adjacent to theta. So I can find theta with the inverse tangent. So I'll do the inverse tangent of opposite divided by the adjacent. So 3.4 degrees. Tangent inverse is arctangent. Arctangent is another word for tangent inverse because we realize that writing tangent inverse with a -1 exponent is going to make people think of cotangent, because that's where we put the exponent on tangent. There are a few places in math where we made very bad decisions about how we should use our notation, and this is one of them. So this is one of those places in math where you just have to get used to it. It's kind of like interval notation with parentheses. There are alternatives to indicating intervals with something other than parentheses, but we still do it. My favorite is the backwards for open intervals using a backwards square bracket. But then again, we also use square brackets for things like matrices. But then again, matrix with no commas, matrix will not have any commas, whereas the interval will have a comma. Usually we don't worry about it too much because it's clear from context which one we're talking about. Any questions? So I think, if I recall correctly, we wouldn't list the 3.4 degrees. That's our direction. It's 3.4 degrees north of due east. I think headings are supposed to be measured from due north. So I'd want to subtract this from 90 and say it's 87 or 86.6 degrees east of north. But I don't fly planes. I have enough trouble with 2 dimensions. I also like dealing with 2 dimensions because it is impossible to be lost in 2 dimensions. If you just travel randomly, you're guaranteed to end up being back where you were, where you started from. Eventually. In 3 dimensions, you can get lost. So here's just a quick example and how we would use components to solve a problem with vectors. Any questions?
Professor, sorry, but how did you get 20 square root 2? It's 40 cosine 45.
Cosine of 45 is root 2 over 2.
Oh, got it.
So I just divided with 40 by the 2. All right. Let's talk about more vector operations. So we had a couple of vector operations already. We talked about vector addition, how to add vectors. So there's vector addition. We take a vector plus another vector. And we talked about scalar multiplication. Where we take a constant or a scalar and multiply by a vector. These two work exactly how we think they should work. But we have two other vector operations. There are two kinds of vector multiplication. So there are two kinds of vector multiplication. There's a multiplication where we take a vector times a vector and come up with a scalar. And there's a vector multiplication where we multiply two vectors and come up with a vector. And each one will tell us different things about the two vectors. So there's a scalar product and a vector product. And the notation that I used here is what we call the two different kinds of products. So the scalar product we refer to as a dot product. And the vector product we refer to as a cross product. So here are all our vector operations. There's vector addition, there's scalar multiplication, and two kinds of vector multiplication, a dot product and a cross product, a scalar product and a vector product. So we have to know how to compute these two kinds of products. And we also have to know what those products represent. So that's on our list of things to do. How to compute these and what they represent. And this is 13.3. Dot product is 13.3 and cross product is 13.4. For those of you reading along in the book. Actually, it's in those sections of the book, whether you're reading the book or not. I realize that those two things are independent of each other. It's kind of like when students ask the question, do I need to know this for the final? And I finally realized that the answer is technically no. Even if this is on the final, you personally don't need to know it for the final to exist. And I think what the real question is, which means the answer is technically not no, is can I get the grade that I want and not know this information? Because students are always trying to be very efficient. They want to know as little as possible, even though they're spending an enormous amount of time and money to ostensibly learn things. We still are trying to find as little information as possible. I know that doesn't apply to all of you, but every time you're wondering what you can sacrifice as far as what you know, you're trying to know as little as possible. All right, let's first talk about the scalar product, the dot product. I'm just going to write down what it is, the dot product. So there are a few ways to compute the dot product, and one of them will even tell you something about what the dot product is for. So let's suppose that V and W are vectors. One way to define the dot product is to say that V dot W is the scalar V1 W1 plus V2 W2 plus, I'm going to stop at 3, where V1, V2, and V3 are the components of V, and W1, W2, and W3 are components of W. Then I'm going to realize I shouldn't use bullet points when one of our operators is literally a dot, also a bullet point. So here's one definition of the dot product. So if I have a vector V, is 5i minus 2j, and W is negative 3i plus 4j. Then V dot W is 5 times negative 3, multiply the I components, plus negative 2 times 4, multiply the J components. If there were K components, I'd multiply those as well. And then just add them up into the scalar. So negative 15 minus 8 is negative 23. Wait, is that right? Jim Carrey going to be all worried about this one now. So here's one definition of the dot product. I haven't told you what this number represents. I just said this is a thing that we can do to vectors to combine them with this thing called the dot product or the scalar product. It's a way we can multiply vectors and come up with a scalar. There is another definition of the dot product. We could say that v dot w is equal to the magnitude of v, that's a scalar, times the magnitude of w, another scalar, times the cosine of the angle between the vectors. So theta is the angle between the vectors. So if we know the angle between the vectors, we can compute the dot product, or if we have two vectors and we want to know the angle between them, then we can use the dot product. So cosine of theta is a scalar, magnitude of v and magnitude of w are scalars. So if I want to solve for theta, I'll just first divide by the magnitudes of the two vectors and then find the cosine inverse. So our favorite thing to do with this definition is to solve for theta, the angle between the vectors, as cosine inverse of v dot w divided by the magnitude of v times the magnitude of w. Missing one. Tend to miss this last one, this last parenthesis, because the TI-84, when we're calculating cosine inverses, when we're calculating cosine, when we're doing a lot of functions, it opens up the parentheses for you, but it doesn't care if you leave off the, if you close off, if you close off the command or not. So let's take the example that we had before, where we have these two vectors. We have their dot product. We computed it with the algebraic definition. And let's find the angle between the two vectors using this other definition of the dot product. So for example, if v is 5 minus 2, 5i minus 2j, and w is negative 3i plus 4j, we can calculate the magnitude of v, and that'll be the square root of 5 squared plus a negative 2 squared. So 29, square root of 29. And we can calculate the magnitude of w, which will be the square root of negative 3 squared plus 4 squared, and so that'll be 5. And I already had v dot w from our first calculation. So I can use this to find theta. Theta will be the cosine inverse of v dot w, which is negative 23. Well, I didn't color code anything. Dang it. Divided by the magnitude of v, square root of 29. Oops. Change one thing about how you usually do your notation. It messes everything up the rest of the day. Times the magnitude of w, 5. And I'll type it in nice single line syntax because that's what we're going to be punching into our calculating machine. So I'll cosine inverse is negative 23 divided by the product of 5 times the square root of 29. Close the square roots, close the denominator, close the cosine inverse. 148.5 1.7, let's call it 149. Any questions? So the dot product is a scalar. If we look back on our original definition, v dot w, just multiply the corresponding components and add. Since we're making this a component operation where we multiply the components and then just add the results, that's what's giving us a scalar. We're setting it up to produce a scalar. So the dot product is set up to produce a scalar. We're only getting one number out of it, so there's no way we can get a direction. Finding the magnitude of v is just the distance formula. It's the square root of the sum of the squares of the components. So the dot product is not going to give you any kind of displacement. It's just going to give you a scalar. One thing that we can note based on the dot product, another way that we can use this geometric definition of the dot product is to note that if the dot product is equal to 0, if we get a dot product that's equal to 0, the magnitude of v can't be 0, or if v and w are non-zero vectors, then the magnitude of v and the magnitude of w are not going to be 0. And so if the dot product of two non-zero vectors is equal to 0, that means cosine of theta must have been the part that's equal to 0. And if cosine of theta is equal to 0, that means theta must be 90 degrees or pi over 2 radians. And that means that v and w are perpendicular. So one thing that we want to note about the dot product, if v is not 0, and w is a non-zero vector, and v dot w is equal to 0, notice that these two zeros here are 0 vectors, and this 0 is the 0 scalar. Then v is perpendicular to w. Another word that we use for perpendicular is orthogonal. So if v and w are non-zero vectors, then their magnitudes are also will not be 0. So if the dot product is equal to 0, that means it's the cosine of theta that must be 0. Because if a product is equal to 0, then one of the factors has to be 0. If the first two factors are not 0, then it's the third factor that must be 0. So we just need practice calculating the dot product and then knowing that it can be used to tell us the angle between the vectors. Or if we have the angle between the vectors, we could use that to calculate the dot product. So this word is orthogonal. Right. Let's talk about the vector product or the cross product. So this is a vector product. I'll make that note before. Here, we're going to multiply the two vectors, find the cross product of two vectors, and we will get a vector. So here we have the cross product. All right. So let's start with a couple of vectors, and let's start with vectors in R3. Let's let V and W be vectors in R3. So V is, say, V1 I hat plus V2 J hat plus V3 K hat. Notice that V1, V2, and V3 are all scalars. They're the IJK components of the vector V. And W is going to be W1 I hat plus W2 J hat plus W3 K hat. So V cross W is going to be a vector. Let's describe what this vector is first. So V cross W is going to be a vector that is perpendicular to V and W. This is why what we find interesting about the cross product. When we do this cross product business, V cross W is a vector that is perpendicular to V and W. So V cross W first of all, it's a vector because this is the vector product. And it's a vector that is perpendicular or orthogonal to V and W. And the direction is going to be subject to what we call the right-hand rule. So if I have two vectors, V and W, I'm going to draw this sort of 3D. Let me write down. If I've got a vector V and a vector W, then V cross W will be perpendicular to both of these vectors. V cross W will be perpendicular to W and also perpendicular to V. So there's another vector that is perpendicular to both v and w that would face downward. So we have to be able to figure out which one that is. So we've got to be able to figure out which of those vectors we want. So this is going to, the direction will be subject to what we call the right hand rule. So the direction, there's someone out front, and that they were having a conversation on the street, and this is very upsetting. Colson's like, well, hey, you be quiet. We're trying to do work up in here. So the direction is subject to the right hand rule. Direction So the direction is subject to what we call the right hand rule. This is the same thing that we use for screwdrivers, lefty loosey, righty tighty. You put your fingers of your right hand in the direction of the first vector listed, and you curl your fingers towards the second vector. So I would point my hand in the direction of V and curl my fingers towards W, and that tells me that V cross W will be going up. So you point in the direction of V with your right hand and curl your fingers towards W. And that will be tell you the direction of V cross W. So the important thing to recognize is that if we take that V cross W, the cross product is not commutative. If I do V cross W, I have this vector pointing up. If I do W cross V, that's going to be a vector pointing down, because I'll point my fingers in the direction of W, and then I'll curl them towards V, and that'll point down. So the important thing is that V cross W will give us a vector that's orthogonal to V and orthogonal to W. We have to remember that there are two vectors that are two directions that are orthogonal to V and orthogonal to W. So the bigger observation here is that if I have two vectors that are not collinear, I'm building a plane, and the cross product will be a vector perpendicular to the plane. We can practice the direction thing as we go. The important thing is we're making a vector perpendicular to two other vectors. So another important takeaway for us, especially in multivariable calculus, where we might want to find, let's say, the equation of a plane tangent to a surface at a given point. Note that we can describe a plane with a single vector. So in R3, if we have a vector that's perpendicular to a plane, we can use the plane to describe the vector. We can also use the vector to describe the plane. So an important takeaway, if we have a plane in R3 and a vector perpendicular to the plane, the plane describes the vector and the vector describes the plane. The plane describes the vector and the vector describes the plane. So if I've got a plane in R3, like this piece of paper, it's not quite paper, but if I've got a plane in R3 here, I can describe this plane by saying this plane is everything perpendicular to this vector. My pen is a vector. I'll point it right at the camera. That's too threatening. I'll have it over. So we need to learn how to make this calculation, how to figure out what this vector is going to be. But I wanted to introduce you to the concept of the cross product, where we're making a vector perpendicular to the two vectors in the product. This only seems like a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. So it's time to practice, I guess. So the dot product is covered in the problems in 13.3, and the cross product is covered in the problems in 13.4. So you can take a look at how to calculate the cross products, but tomorrow that's going to be our project. We're going to look at how we calculate the cross product. Any questions? Comments? Deep thoughts? All right, and that's going to do it for today. We introduced two new operations on vectors, the scalar product and the vector product. We have a vector times a vector can be a scalar, that's the dot product, and a vector times a vector can be a vector, that's the cross product. So we have those four different operations on vectors. All right, so that's going to do it for today. I will see y'all on tomorrow. We'll do some cross product calculations. Everybody have a good day, and thanks for playing.